There we go. Thanks for reminding me. Reshare my screen and then. So yeah, acids and bases. Right, so we're just coming out of reactions. Two of our really important substances that we look at reactions a lot with are acids and bases. And you'll kind of see why they're a little bit more important. Um, so we have like three types or definitions of bases. Tiger, you want to take these?
Sure, yeah. So, this is the different definitions for acids and bases, right? Arrhenius, Bronsted, Lowry, and Lewis. So the Arrhenius definition is that it increases the ion concentration in an aqueous solution. That is, it will disassociate itself and then increase that concentration. Bronsted Lowry is that it either accepts or donates a proton, while Lewis is that it accepts or donates an electron pair. And while you're going to be seeing like all three of these, and you should definitely know all three of them, um, you'll probably see Bronsted Lowry the most, but obviously still get a good grasp of all three of them.
Yeah, I will say Lewis bases, acids and bases are a lot more complicated and probably won't deal with them too much. Mostly be about these two. But yes, so I think this is like the most basic thing we can look at here. Where with acids and bases, we're just kind of talking about ions dissociated in aqueous solutions. Um, so with acids, the key, do I have this here? If I, yeah, okay, I do. So the thing with acids and bases is that when they're dissolved or when they dissociate in aqueous solutions, is that there are two specific ions that they will give off or increase the concentration of when they dissociate. That's like the key thing about acids and bases that kind of give them a lot of their properties. So those two ions, I really hate Google Slides formatting here. It's kind of hard to read, but the key with acids is that when they're dissociated in an aqueous solution, they're going to give off hydrogen plus H plus ions. Another name for that would just be protons. Um, if we're looking at a hydrogen atom, it's literally just one proton, one electron. Most hydrogen doesn't have a neutron. So if we're just looking at one proton, one electron, and we have an H plus ion, it's literally just a proton. Um, so when acids dissolve, they will release these H plus ions. And the key here, you'll notice that this is aqueous solutions. Uh, that's because this H plus ion, this hydrogen cation, will bond with the water to form this ion. Does anybody know the name of this? It's H3O plus. No? Anyone want to hazard a guess? I guess if you don't know, it's like a guessable thing, but so this is H3O, has a charge of one, obviously. And this is known as hydronium. Um, put that in here. Hydronium. Um, I think that's a cool name, but that's just me. Um, so this is the important part of why it's an aqueous solution, because when the acids give off that proton or that H plus ion, it will bond with the water to form these hydronium ions, and those hydronium ions are that's the ion concentration Ernest is referring to here with acids. Bases give off or it's actually kind of, I did this here. Bases give off a different ion. Does anyone know what bases give off? The name of it? Um, Dissolve into some compound plus a,
Dioxide?
yes, hydroxide ion. So that's this over here. It's an OH minus. So it's just one oxygen, one hydrogen. It has a charge of -1. You can see it as hydroxyl when we're taling about like functional groups in organic and biology. That's more when it's bonded to some other hydrocarbon kind of thing. But here, when it forms this ion, here it's going to be hydroxide. And this is one of the polyatomic ions that you should get familiar with. Yeah. So we look here with the acids, this hydrogen ion bonds with this water to form this hydronium. What's interesting is that water itself can basically be broken up into a hydrogen H plus ion and a hydroxide ion, right? If you just do this, it's H2O. That's water. And that's a really important property of water, which is why it has a pH of 7, which is why water is neutral, right? Pure water will be chemically neutral. It's because of this property, and you'll see why in a second, I think. Um, we have not gone over stoichiometry yet, so we will skip this for now. Yeah, we'll skip this for now. So let's look at pH and pOH. Tiger, you want to explain these?
Sure. Hold on, my Wi-Fi's set up again. Okay, cool. So, pH is a measure of the acidity of a solution, while pOH, POH for hydroxide, it's basically the pH scale, but it's reversed, right? So it basically finds the alkalinity of the solution, basically how basic it is. Some equations relating it to. So pH is the negative logarithm of the concentration of H plus ions. That's just a natural logarithm. If you know, you know. If you don't, then it's fine. Same thing works for pOH. And then one thing to remember is that pH plus pOH is always equal to 14. So they give you pOH, and it's like, what's the pOH of this, right? You just subtract for that from 14 and the pH.
Yeah, so pH, some people think, I mean, we don't, I mean, it's like not an importantly rigorous term what it stands for. It could be power of hydrogen, potential hydrogen. And then obviously OH, you have the hydroxide, as Tiger was saying. Um, so these just measure, yeah, the acidity or alkalinity. Yeah, alkaline. Yeah, okay. Of a solution or some specific substance. The key here is just it's just the negative of the log of the concentration. We use a negative because obviously it's going to be less than 1. So yeah. Um, which I don't know how many of you have done work with logarithms before. But yeah, I think usually these will be represented in scientific notation with uh, to the power 10 or 10. So I think oftentimes you can just do log base 10 for these. Um, but yeah, so don't know how much of the math you're probably going to have to do, and probably won't be too much actually applying this. But it's more conceptually just, what does pH represent? Just measures, it's a measure of the concentration of those H plus ions, right? We go back, right? We are just increasing the ion concentration. So obviously the more acidic something is, the higher the concentration of H plus or hydronium will be. And so that pH will be lower because it's a logarithmic scale. So it's and then pOH is just again the backwards. So yes, the key here is that pH and pOH will form that 14 on the scale. And so I don't think we should do pKa yet. Yeah, probably not. But I was kind of hinting at earlier about this, why water was important for this, why water is neutral, right? Um, oh, yes, of course. Yeah. So why water is kind of important for this is that water is perfectly neutral, pure water is perfectly neutral because of, hold it, this property here, right here. Right. So if we look at this, This is water, right? And remember we were talking about equilibrium, right? How you can have forward and backward rates of reaction, right? Um, well, it's the exact same with this reaction here for water, right? So in the forward, it's usually in the other way around. In the forward, you can have this H plus and this hydroxide combining to form this water. And in the reverse rate, or reverse reaction, you can have water decomposing into these two. Um, and so notice that when the water decomposes into these two will now increase the ion concentration. But notice that it increases the ion concentration in equal amounts, right? If water dissociates or uh, splits into these two, it decomposes, that's what I was looking for, into H plus and hydroxide, then you're increasing the ion concentration of both H plus and hydroxide equally, right? Um, and so what that leads to is the fact that water won't ever increase water won't ever increase the number of H plus ions more than it will increase the number of hydroxide ions. You think about that, it's not really net increasing one particular set of ions, which is why you can kind of consider water as neutral. It won't ever increase the amount of hydronium, and it won't ever increase the amount of hydroxide relative to each other. Here is Bronsted-Lowry definition, right? Accepts or donates a proton. This reaction right here is literally just accepting or donating a proton. Right in the forward, it's again, this is backwards. In the forward, it is accepting a proton. In the reverse, it is donating a proton. And so what you kind of get to is this idea that water is somehow both an acid and a base because it's increasing the amount of H plus. It's also increasing the amount of hydroxide. It's donating a proton, but it can also accept a proton. And this Lewis definition also hinges on that same fact. Um, and so what you get to is this concept that water is both an acid and a base. But really, what's going on is the fact that water is just perfectly neutral. And that's why for these definitions, for the definition of an acid and a base, it has to be dissociated in an aqueous solution. Um, oh, that was the other cool thing about this with water. Um, right, we were talking about forward and reverse rates of reaction. Um, that forward and reverse rates of reaction, you will get to this concentration of times 10 to the negative 7, which you'll get basically your pH of 7 here, your pH OH of 7 here, and that's how you get your 14. And that's why water is chemically neutral. Very, very interesting. Okay. Questions on I think you guys seem pretty good through here. Questions on this part, the pH and pOH. Um, Again, I know you probably haven't done too much with logarithms, so just kind of understand conceptually how pH and pOH are done, and then if you want more math on it, we can of course do that. Are we all good on pH and pOH? Okay. Guys want to? Oh, I guess we can mention the strong acids and bases. Um, so here, wait. Real quick warning: this meeting will end in like 4 minutes. When that like the Zoom thing will end in 4 minutes. When that happens, just join back. It's the same link. And we will continue. Um, so for good on like these definitions for acids and bases, we can kind of get into like some specific ones and like the important ones you need to kind of keep in mind. Crap, sorry. Wasn't this one, it was this one. Sorry. These are a lot of like compiled ones from uh yeah. Okay, so Second, you want to explain strong acids, strong bases?
Sure. So, as we learned, strong acids, according to the the definitions that you'll find the most, it it gives us its hydrogen, right? It gives it up to whatever it's in a solution with. So, what strong acids do is that they will 99.9% disassociate. Like they disassociate so much that um it's not really reversible. You wouldn't write it as an equilibrium reaction because it's so far weighted on the right. So these acids will all completely break up into, for example, hydrochloric acid H plus and Cl minus, hydroiodic H plus, I minus. You guys get the point. Um, Something to note here that is that sulfuric acid H2SO4. While it does have two hydrogens, it's only a strong acid for the first hydrogen, if you know any. So after it gives away that first hydrogen atom, it's no longer a strong acid, it's actually a weak acid after that. And the same idea applies for your strong bases, right? You got that you have the hydroxide, and all of these will completely disassociate into their respective ions, like Li Li plus and then OH minus, Na plus, OH minus, and you guys get the point.
Um, so, like we were saying, these will dissociate almost completely, if not completely, in aqueous solutions. You should probably memorize all of these for science pool. They're pretty important. Because they also get into like the concept of electrolytes, where you can distinguish what's a good electrolyte versus what's a bad electrolyte or weak electrolyte, depending on so whether something's a strong acid or a weak acid. Oh yeah, weak acids, weak bases will literally just be anything that's not a strong acid or a strong base. So, um, just that I find easy way to memorize these is like in this order, right? So if your hydrogens with your halogens, chloric, iodic, bromic. Um, then you have ClO3. If you guys have been looking at your polyatomic ions, what is ClO3?
Chlorate,
What is it? What is it? Sorry.
chlorate,
Yeah, chlorate. And so here we have chloric acid. Here we have perchloric acid because ClO4 would be perchlorate. Sulfuric acid, right? So these two, obviously, you're just adding one more oxygen. Sulfuric acid. This is obviously very popular. I mean, no, it's well known. Sulfuric acid. A lot of fun uses for that one. And then nitric acid's just weird. Don't worry about it. I mean, like memorize it. Don't